This is an interesting problem. The problem is to find the sum of the inverses of the cubic powers of natural numbers. 1 plus 1 over 2 cubed plus 1 over 3 cubed, etc. So we want to sum it up. So if you look around, it's all there is a formula, in fact, for all even powers of inverses of natural numbers can be summed up. I have seen a proof in Ramanujan, so I don't know whether the formula is due to him or not. In any case, this is the formula for S2n. Here, B is Bernoulli number, so you have to deal with that. But that's look up. You can look it up. So if you plug in the Bernoulli values, and you can also prove this using Fourier series, etc. This is a well-known result. 1 over k squared sum is pi squared over 6. 1 over k4 sigma k equal to 1 through infinity is pi 4 over 90. The question is, what is 1 over 3? So that's 1 cube powers. So if you simply sum up 3 terms, you get 1.1620. So we already get a result. S3 is greater than 1.162. Of course, we can keep summing, but how far are we willing to go? To get a lower bound, you can look at this way. So if you have, I'm going to draw the curve y equal to 1 over x cubed. And then, so let's say this is 1, this is 2, this is, so if you look at these areas, this is what we want to compute. 1 plus that, because this height is 1 over 2 cubed. So this is the second term, third term, fourth term, etc. So from this graph, we know that S3, so if you start from here, this gives you, this area gives you 1 over 2 cubed. This is 1 over 2 cubed. This is 1 over 3 cubed, etc. So S3 is 1 plus these areas, but these areas is less than the integral from 1 onward. So this is less than the integral 1 to infinity 1 over the area under the graph. So that's going to be 1 plus, this is minus 1 to x squared, 1 to infinity. So that's 1 plus half equal to 1.5. So we know definitely a sloppy result is S3 converges, and of course it is less than 1.5. So the question is, how do you make this better? I mean, another, of course, a way to make better is you add a few terms and do this integration from, so let's add 3 terms, which we already summed up here. So another way is S3 is less than this plus this plus this. So we are here, up to here we are going to, 3 terms we are going to do it physically, which is 1.162 plus the integral from this point, 3 to infinity 1 over x cubed dx. So that's going to be 1.162 plus 1 over 2x squared, 3 to infinity. So that's 1.162 plus 1 over 2 multiplied by 9. And that will turn out to be whatever. It will be, I think, somewhere around somewhere 1 point, whatever you can compute. So you can get a slightly better lower bounds, etc., upper bounds. And so to find something a little more elegantly, I thought of something. So maybe this is all around. I know there are bounds for this, so I'll comment on that a bit later. So again, let me draw this curve 1 over x cubed. And so we have to compute this. This is 1. We have to compute this. These areas is what we need to compute. So what we can easily compute is the area under the graph. But then the problem is that that's only a poor approximation because of these blank regions. Right? So question is, how do you address some more of this? So this is 2, 3, 4, etc. So if it is n, so this is n minus 1 n. So I want to get a, I'm going to expand that here. Say, let's say this is uh, n and n minus 1, and then, or let's say k minus 1, it doesn't matter. And so this area is what we are interested in. We can compute this area easily under the graph. So to accommodate this, I'm going to draw a tangent through this point. Remember, this is a straight line. I'm going to call it y equal to mx plus c. And my goal is, if I can figure out this height, then I can compute this area. So it's a baby step. So this area plus this area is a better approximation to the area under the triangle, and that way we will see how much this improves. So I'm going to draw a series of tangents like this from this point. So then the idea is, on top of that, I'm also going to uh, include this triangular area. So it's a, and then because the only thing I can compute is the area under the curve, then I'll come from that, I'll subtract the area under the triangles. That will give you a better approximation for S3 that we are looking for. So if I call these points A, B, C, D, E, and so I want to compute this area of the triangle CDE, and AB. So of course AD is the same as. So question is how to find this height. I know the total. Let me call this point F. So I know the total height is the height AD. AD is the same as BC, which is 1 over k squared. And so I know the value of here. This is 1 over k squared. This is 1 over k minus 1 squared from A to F. So let's look at the line y equal to mx plus c. So the slope y is dy by dx. I'm going to evaluate this at x equal to k. That's so that's going to be same as the slope of this curve. That's the whole my whole point. So that's the same as d by dx of 1 over x cubed, which is minus 3 by x4. And I'm going to substitute x equal to k. So the slope is minus 3 by k4. And once again, the graph is y equal to, so minus 3 by k4 x plus c. So now let me substitute that point again. So y is, we know the height, we know the value of x is k, and y is 1 over k squared. So at that point, y is 1 over k cubed, rather, is minus 3 by k4 multiplied by k plus c. So this you can see k cancels, so you get 3k3. So you get c to be 4 over k cubed. So we got this equation of this line completely. So the line is now y equal to minus 3 by k4 x plus 4 by k3 is this line y equal to mx plus c. So this is A, B, C, D, E. So now let's go to So let's see how much is AE now. So AE is going to be where this line intersects at x equal to k minus 1. So to get AE, you put uh, x equal to k minus 1 into this line, x equal to k minus 1. So AE will be minus 3 over k4 multiplied by k minus 1 plus 4 by k3. So if I expand, this is minus 3 by k3 plus 3 by k4 plus 4 by k3. So this and this cancels, giving us 1 by k3 plus 3 by k4. So that's AE from here to here. So what we are interested is DE. So DE, the height of the triangle, is AE minus AD. But A is 1 over, A is the same as BC. This is 1 over k cube. So that's 1 plus k cube plus 3 by k4 minus 1 over k cube. So we get lucky and we can figure out this height. And this width is 1. So the area of the triangle is now known. So the small triangle area of CDE is half multiplied by base multiplied by 3 by k4. So that's 3 by 2, 1 over k4. And with that, we can try to compute the, so I'll go back here and I'll try to compute, I'll use this to make use of the approximation. I'll compute this area from some point M onwards. So this, the whole idea is that the area under the triangle or area under the curve is greater than the triangle, because you can see there is some gap. So what we want plus, so if you add what we want, which is this shaded series plus the red region, that is still less than the area of the triangle. So let me write down an equation. So we get the what we are interested in, S3 k equal to, but I'm only going to start from some M. And then you have 3 by 2. So this term is just these green regions. Then 3 by 2 summation 1 over k4, k from M through infinity. So that's the red region starting from some M onwards. And that's less than the area from here, which is M minus 1. This is where we are starting. But if this is M, then it starts from, or N starts the A. So this is less than the area from M minus 1 to infinity 1 over x cubed dx. So this is minus 1 over 2x squared, M minus 1 to infinity. So you get 1 over 2 M minus 1 squared. So the interesting thing is this we can sum up this. So what we are interested in from here, 1 over k cubed, k equal to M through infinity is less than 1 over 2 M minus 1 squared minus 3 by 2, this sum, k equal to 1 over k4, k from M through infinity. But this is related to pi 6 over, so I'm going to write this up. So what we are interested in is actually k equal to 1 through infinity, 1 over k cubed. So that's going to be 1 plus, you just add up those terms on this side, up to M minus 1 cubed. This we are going to do it by hand for any M, plus 1, that's my approach. So however you get, how far you want to go. You want to stop at M equal to 2, that's fine. Minus 3 by 2. So this is 1 through infinity minus a few terms. So what 1 through infinity is pi 4 over 90, minus 1, minus 1 over 2, 4, etc., minus 1 over M minus 1, 4. So again, this we'll do it by hand. That's the end of it. So that's I'm just going to approximate this. So let's say we do it for m equal to 5 or something. So if you do this for m equal to 5, so remember this is not this is less than, this is still less than. So if you use m equal to 5, this will turn to be less than 1.2035508. And I did one more term, m equal to 6, you get 1.2021248496. So we can add a couple more terms easily, but I just stopped there. So what I'm trying to say, so we can easily say uh, this is less than 1.202124. And I have seen somewhere that you may be able to improve this by up to 1.20205. I don't know how many more terms you have to go. Or another way is, remember, right now we are just drawing a tangent and taking this area. So we this is what we are interested in. We are able to accommodate this area on top of that. So it's a little improvement. But I see you can draw another tangent here, but it gets complicated. And if you can somehow figure out this area, let me draw it another color. Let's say this area, then that's a better approximation, because then this 1 plus 2 plus 3 is still less than this curve. So that may be a way to go. In other words, if you can draw a tangent here, of course you can draw the tangent and let them interact, and you can. So the whole point is to approximate this area below the curve more and more, so that the approximation gets better. So anyway, if you use the 6 terms on this approach, you get this. So the you can say, so the result is certainly less than 1.2021. So how much less, or can you get an exact expression? These are the things to look into. It looks like the odd terms cannot be summed. I haven't seen any, and I don't know the exact reason why. In other words, odd powers of the reciprocals, except the first one, of course, is infinite, but on 3, 5, etc., it looks like there is no closed form solution like for the even powers. But certainly you can improve upon these approximations, the simple geometric approach. Thank you.